Okay, now I'm happy to do the first example in this course. Course. Sorry, my English is not perfect, but I love doing this. So, in the foreign language. So let's do the example. Now, I left this from my previous video, but I'm going to, clean this up when I explain what's going on. So here, I don't know if you can see very well. The example 1 says, figure 1, so this is figure 1, represents the magnetic circuit of a primitive relay. The coil has 500 turns and the mean core path is equal to ILC is equal to 360 millimeters. So this core length, even here, the mean core length, so the middle line is equal to 360 millimeters. When the air gap lengths are 1.5 millimeters each. So here we have an air gap and here we have an air gap, which both are equal to 1.5 and 1.5 millimeters. A flux density B of 0.8 Tesla is required to actuate the relay. The core is cast steel. For A, find the current in the coil here. Or B, compute the values of permeability and relative permeability. This PR and here dot is shortened for permeability of the core. And C, if the air gap is 0, find the current in the coil to the same flux density 0.8 Teslas in the core. So now, because the example say that this core here is a cast steel, you have to look at the figure of the magnetization curve. So this is from the book, what I have, but you can find it everywhere, the magnetization curve of the cast steel. So you have to look at this figure to know what is the amount of the magnetic field intensity when you have 0.8 Teslas. So looking at this magnetization curve, you don't have to worry about this. We get that for 0.8 Tesla we have to have a magnetic field intensity of 510 ampere turns per meter. So the flux density of the core is 0.8 Teslas. So we have to have a magnetic field intensity in the core that is equal to 500 Tesla ampere turns per meter. So in the core, not in the air gap, you have to realize that. So I'm going to clean this figure table now, and so I can have the room to write down the formulas and you all need. Okay, so now if we know what is the magnetic field intensity in the core, we can calculate the MMF, the magnetomotive force of the core, which is equal to FC is equal to the magnetic field intensity of the core times the length of the core, mean length of the core. So this is the first thing you need to calculate. And this is equal to 184 ampere turns. So when you do this, you have to bring this to the basic units. So this would be 0.36 meters. Okay, now we calculated what is the MMF for the core, but we have to calculate what is the MMF needed to magnetize the air gap. Well, the formula for that is Fg is equal to Hg times the times 2 L. Why 2 times the length of the air gap? Because it says that the air gap lengths are 1.5 millimeters each. So we have here 1.5 millimeters and here. So that is 2 times 1.5 millimeters. And what is the problem here? Well, we don't know what is the magnetic field intensity in the air gap. But if you watched my previous video, you would know that BC, the B of the core, is equal to the B of the air gap. And the formula for magnetic flux density is equal to mu 0 mu r times the magnetic field intensity. Mu r of the relative permeability of the air is equal to 1. So when I transfer mu 0 on the left side, you get that Hg, or the magnetic field intensity, is equal to the magnetic flux density divided by mu 0 times 1, but I'm not gonna write times 1. So F magnetic motive force is equal to, instead of Hg we write Bg divided by mu 0 times 2 times length of the one air gap, and we get 1910 ampere turns. So now, I don't know if you can see, but does this say something to you? Well, for the core we need much less magnetomotive force to magnetize the core to have 0.8 Tesla in the magnetic core. But for the air gap, even though it is much thinner than the length of the core, you see that we need 10 times in this situation, 10 times more magnetomotive force for magnetizing the air gap to have 0.8 Teslas here. So the equivalent magnetomotive force we need is equal to the sum of the magnetomotive force of the core plus the magnetomotive force of the air gap, and you get 2094 ampere turns. Now, because F equivalent is equal N I, number of turns time is the current, the I, the current in this current, in the coil, sorry, the current in the coil is equal to F divided by the number of turns. And you get about 4.19 amps. So we figure out A. Now let's figure out the values of permeability and relative permeability of the core. I'm now going to clean everything except these two, and I'm gonna leave this one. Now, if we know B in the core and H in the core, it's easy to calculate what is the permeability of the core. Now look at this. B of the core is equal to mu of the core, permeability of the core. This is not relative permeability, times the magnetic field intensity. And now you see that mu of the core, the permeability of the core, is equal to B of the core divided by the magnetic field intensity. That is 0.8 divided by 510. We get 1.57 times 10 to the minus 3 Henry per meter. Now, how can we measure the relative permeability of the core? Well, it's easy. Mu of the core is equal to mu relative of the core times mu 0. We always have mu 0. And now mu r, the relative permeability of the core, is equal to the permeability of the core divided by mu 0. We have 1.57 times 10 to the minus 3 divided by 4p 10 to the minus 7. This is a constant, and is equal 4p times 10 to the minus 7, and we get 1250. And the mu relative permeability doesn't have a unit. And now we calculated the permeabilities, and now it says if the air gap is 0, so this is now connected, the right side is now connected physically on the left side here. Find the current in the coil to the same flux density, 0.8 Tesla in the core. Now I'm gonna clean this up. Now we have another situation where this is connected here. Now there is no air gap, and the mean length is equal to 360 millimeters. So in that situation, when this is connected, and this is LC, the main path of the core, it's easy to calculate now because there is no air gap, there is only one medium, so the magnetomotive force is equal to AC times LC. Because there is no any, this is the only medium we have, that's the cast steel, and that was equal to 184 ampere turns, and that was Ni is equal to this magnetomotive force, and then you get the I, or small I, is equal to F divided by N, and that is equal to 184 divided by 500, and all of that is equal to 0.368 amperes. Now, fun thing now is that you know how much you need to give to invest current when there is no air gap, and now you know how much you have to invest for the same magnetic flux density with the air gap. So this is the current we needed with the air gap, which is much larger for the same magnetic flux density, and this is the current, let's say it's I, small I. Now this is the current that is needed to magnetize this core without the air gap for the same amount of magnetic flux density. That's a huge, that's important to know, because generally we don't like air gaps in electrical machines, but we can't avoid them in the rotational mechanical machine, in the machines where there is mechanical energy. Fortunately, transformers don't need no air gaps and no mechanical parts. So, but the other ones that we are going to learn and that are learned in electric machineries, air gap is a huge problem. Oh, thanks for watching. I'm a little bit tired, and see you in my next video where we are going to do one more example.